Hello, WMC. Welcome to the second Arduino Acclimate workshop. Today's lesson is Introduction to Circuits.
Hello, everyone. Thank you, Courtney, for organizing this event today. My name is Raunaq Chopra, and I usually go by Ron. And I'm going to be leading the workshop on Introduction to Circuits today. So a little bit about myself before I dive into the more technical stuff of the presentation. I'm a master's candidate in the Department of Electrical Engineering here at the University of California, Davis. And I currently work as a teaching assistant for this course ENG3 that the Bio and Agriculture department teaches. This is a course very similar to the things we're going to be talking about today related to circuits and programming using an Arduino. There's a creative design project at the end of the term, which we design using these same elements here, the circuits, and program it using Arduino. And we're focused towards communication and engineering. So we work in a lot of teams and groups and that kind of thing. I'm also currently doing research in the R Lab, which is led by Professor Marina Radulowski, and my research is about quantum simulator models. And a little bit aside from my professional life, personally, I like to travel. I'm an avid reader, and I enjoy creative writing. So let's talk a little bit about what a circuit even means before we even start talking about electronics. What does the term, in the English term, circuit mean? So it is a roughly closed path. And if we think about it from the dictionary standpoint, dictionary.com gives this definition for a circuit. For us, the more useful definition is this one right here. The circular journey, or one that begins or ends at the same place, or round. So how does this definition apply to a circuit, or an electronic circuit rather? In electronics, the term circuit refers to a closed path for electric current to flow around. So over here, we see there's a closed path over here, and these arrows represent the path along which electric current flows. So we'll talk a little bit more about electric current in a few slides, but for now, these arrows are representing the direction in which current is flowing. So that is the very fundamental definition of what a circuit is. Let's talk a little bit about what makes circuits work. So here I have a very simple circuit right here. This is a 1.5 volt battery that is connected to a light bulb over here. So one of the primary things that you see here is that we have a battery or a source of power, which is providing voltage. So that is one of the things that is going to make the circuit work. How does that do that? So batteries, just like I said, provide energy to carriers or electrons, which are going to be moving around in the circuit to be able to make the circuit work. Now, when we talk about something as small as electrons, our usual units of energy don't work that well. Usually we are used to measuring energy in joules, but joules is a very large unit when we talk about electrons. So what we do is we come up with a separate unit, a much smaller unit of energy. It's called the electron volt. And the electron volt is a very small amount of energy in joules. It is 1.6 into 10 to the negative 19 joules. You might recognize this number as the same amount of charge on an electron in coulombs, but that is the amount of energy right here. So what is the significance of this number? Well, when an electron passes through a 1.5 volt battery, it gains 1.5 electron volts of energy. For that matter, if an electron passes through any number of volts of battery, an n volt battery, it's going to gain n electron volts of energy. So in this case, just for simplicity, and since most AA or AAA batteries are 1.5 volt batteries, I just decided to go for a 1.5 volt battery here. So when an electron passes through this battery, it gains 1.5 electron volts of energy. So these electrons, once they gain energy, what they do is they pass through something to do useful work. In this case, they're passing through a light bulb right here. So when they pass through here, the useful work they're doing is turning on the bulb, right? Once they do that, they're going to go back to the battery after having depleted the energy that they have. They're going to pass through the battery again, and they're going to gain more energy. and then they're going to come back to pass through this light bulb. Now, how long is this procedure going to go on? It is going to be till the battery dies. And what does it mean for the battery to die? Battery dies when it runs out of energy to give to these electrons that are passing through the battery. So once the energy store, the one that the manufacturer put in at the time of manufacturing runs out, we call the battery dead, effectively. So this could be a little bit confusing when you see it for the first time. So what I've done here is come up, or try to come up rather, with a ski lift analogy. So when you go to a skiing resort, you do something similar, but on a much larger scale, right? So circuits can be thought of as ski resorts in which the electrons are the guests visiting a ski resort. And what are they doing? They're going to get onto a ski lift or a battery to gain potential energy. Once they get off the ski lift, well, they're going to have to walk a short distance towards the slope. So what is happening here is getting off the ski lift, the electrons are traveling towards the slope. Once they walk over to the ski slope, they're going to ski down it, and they're going to lose the energy that they gained by going up the ski lift in the first place. Since they're losing potential energy because of going down in terms of height, that is what is happening here. And since we were visiting usually from so far away, we're never going to be done with just one round on the ski slope, right? So what we're going to do is once we get down the hill, we are going to get on the ski lift once again, and we're going to keep going till it is time to shut down the ski resort, or in the case of a circuit, the analogy would be when the battery ends up dying. All right. So now other things that make a circuit work. Resistance is another important quantity. So what happens is when electrons travel through matter, we have to remember that matter is made up of atoms. And when electrons travel through that, they're bound to collide with the atoms. So that means that charges never have a fixed path through any kind of a material that they're going to travel through. Or rather, they're not, not going to have a straight path through what they're going to travel through. So what is the path going to look like? It's going to be something similar to this. So the dark blue circles over here can be thought of as atoms. This much smaller circle hopefully is visible on your screen. And lighter blue is an electron. So what's happening is when a voltage is applied, it's going to travel through here. It's going to bump into these atoms and have a very crooked path through the material. So what's happening is that just like there would be friction on the ski slope, which is going to cause you to stop at the bottom of the slope, you're going to have something that's going to be limiting the speed of your electrons traveling through any kind of a material. So what's going to happen is that you begin with some potential energy, you start converting it to kinetic energy, but when you collide, you lose that kinetic energy as well, right? And when you lose energy, what form do you lose it in? Usually that form is going to be heat. It's kind of similar to how surfaces heat up when rubbing against each other due to friction. It's a similar idea, similar analogy, but not quite exactly the same. So in a way, what the material is doing, it's resisting the flow of electric current. So now, if it's resisting the flow of electric current, and if the atoms are causing the electric current not to flow as effectively, does that really make resistance necessarily bad? And to answer that question, I like to think again in terms of friction. Is friction necessarily bad? Not always. I mean, we need friction to be able to walk and to be able to maintain balance. We can't write on paper if we don't have friction. So it's kind of one of those quantities which is necessary, but which is not always an ideal quantity to have in a system. So resistance in short terms is not necessarily a bad thing. It can be very useful in certain instances. For example, when we talked about the light bulb, which was glowing, it glows because the electrons collide with the atoms of the filament heats up, and the heat is what causes the filament to glow. There are special elements called resistors, in fact, which we often use in circuits for many different applications. So a few examples of applications would be that we sometimes put resistors with LEDs. What that does is Changing the voltage with LEDs can cause the current to change enormously. And if there's too much current that flows through an LED, that's probably going to burn the LED out. So if we put a resistor in the circuit with the LED, the resistor is going to cause the circuit to change current very insensitively, or there's not going to be huge jumps in and there's not going to be huge jumps in the amount of current that's flowing. So what that does is that if the voltage is to fluctuate for any reason, the LED is very unlikely to burn out in this case. And another example is that many modern devices use resistors for what's called biasing. There's an example in a couple of slides where I have a circuit diagram which shows how biasing is done. But for now, and these are just a couple of examples that use resistors, but there are a plethora of examples. Resistors can be found in almost every circuit that you can imagine. All right. The final and one of the most important quantities is electric current, which is what composes of electricity. So electric current is defined as a rate of flow of charges through the circuit. So if we imagine taking a slice of a circuit like so, and if we imagine these to be electrons right here or charges right here, then we measure the amount of current to be the amount of charge passing through this cross surface in a fixed amount of time or in a unit time. So the way electric current works is that voltage causes current to flow. Come to think of it, voltage is the difference in the height of the ski slope on the top of the ski slope versus the bottom of the slope. And current is what happens because of that. The current is the skier going downwards along that slope. All right, so just like a skiing person is going to go down the slope, charges are going to go from high energy to low energy. So how do we determine which direction current flows in? We have a few specific definitions for it. So what happens is that positive charges move from high voltage to low voltage. Negative charges are going to move from low voltage to high voltage. That's just how it works in terms of energy. So if you look at this diagram right here, if you have a positive charge and it's close to the high voltage or the positive rail over here, it's going to take more energy to push the positive charge that way, right? Towards the high voltage. So what it's going to do is to lose energy, it's going to travel downwards towards the low voltage side. On the other hand, for the negative charge, what's going to happen is that it's going to take more energy to hold it close to the low voltage or the negative side or the negative rail. So it's going to spontaneously move towards high voltage. That is the low energy state for a negative charge. So how do we define the direction of the flow of current? It is going to flow in the direction in which positive charges would flow. So if we imagine just for a second that these are negative charges right here, these blue dots are negative charges and they're flowing to the right, the current is in fact flowing to the left in this circuit, right? And if we imagine these charges to be positive charges and they're flowing to the right, the current is also flowing to the right. All right, so if we go back a few slides over here and we look at this diagram, these arrows right here, they are representing the direction of the flow of electrons, right? So if I go back here where I had all this text, you're going to see that each electron gains or gets 1.5 electron volts of more energy. Remember, electrons are going from positive to negative. So going towards negative is giving the electrons more energy. But the current in the circuit is going to be flowing clockwise instead of counterclockwise. All right, so coming back to where we were before, in just a moment. So now that we talked about some of the most fundamental quantities that make circuits work, let us talk about relating these. Now, these are such fundamental quantities that all of electronics are governed by these three quantities: voltage, current, and resistance. So there's going to be some sort of a mathematical relationship between them. To be able to see what this relationship is, we're going to remember that any battery of any voltage is going to increase the energy of an electron by those many electron volts. So 1 volt battery is going to increase the energy by 1 electron volt. So in terms of electronic devices jargon or engineering jargon, what we say is that the electron has gained 1 volt potential. That is, it has gained 1 electron volt of energy per unit charge or per electron. So when the electron passes through the resistive material, remember, it loses this potential energy as heat. So we say that this electron drops in electric potential by 1 volt. So how do we define current? We define current as the amount of change in potential across the material per unit resistance of the material. And this is a very important, this is a very fundamental law in electronics. This is called Ohm's Law. So now let's shift gears a little bit and talk about resistors, one of the elements that are very useful because, and just as we discussed before, resistance is sometimes a very useful quantity. Resistors are elements which resist the flow of electric current. So over here, what I have is a symbol of a resistor that we use when we're drawing electric circuits. So as you notice, we draw resistors as these squiggly lines, and what these lines essentially represent is the fact that electric current has to navigate through this very curvy path. It's not going to be able to accelerate. It has to bend around all these corners. And so this material or this device is resisting the flow of electric current. So as promised, here are a few examples of instances in which we want to use resistors. Over here, I have the symbol of an LED and a battery. So just like we said before, if there's any fluctuations in the voltage of this battery, what that's going to do is it's going to cause the current in an LED to change enormously. Now, what that could do is burn the LED out or cause it to stop glowing, depending on what kind of a fluctuation it is. If the fluctuation causes the voltage to rise, it's going to burn the LED out. If the voltage drops, it's going to turn the LED off. But having a resistor here changes the amount of change in current, essentially. So what's happening is that if there's a fluctuation, the current through the LED doesn't change that much. It continues to glow roughly constantly. So that's an important application of resistors that we see right here. Another example that we talked about before is, and I apologize for the wrong text here, it should be saying that this is a biasing circuit. Over here is what we call a transistor amplifier. And what this basically does is that we put a signal in on this side over here. And on the other side, on this node on the right, the signal comes out amplified. So to be able to amplify the circuit or the signal correctly, what we need to do is we need to set a bias point voltage right here. We need this point over here at the input to be 0.7 volts above this point over here for the circuit to work correctly. And the signal is just added on to those 0.7 volts, and it's usually much smaller in amplitude than 0.7 volts. So what happens is that the signal comes in here, it exits amplified here, and all these 4 resistors are basically playing a role in biasing this device, the transistor, correctly. This resistor over here at the top right is governing how much the signal is going to be amplified. So that's yet another application of resistors in this case. All right, so that is a little bit about some of the examples of where resistors can be used. But as you can notice that many circuits don't have necessarily just one resistor in them. They can have multiple resistors like we have here. So sometimes we need to consider what kinds of connections these resistors have with one another. So there are 2 main kinds of connections which we are going to talk about here. The first kind of connection is called a series connection. So what happens in a series connection is that we take multiple resistors and we put them together in a chain like so. So what is going to happen is that there's going to be some circuit connected around here. Remember, we have to have a complete loop for something to be called a circuit. So what that's going to do is that current is going to be coming from, say, somewhere up here, and it's going to flow down these resistors one after the other. So now what this means is if we have a circuit with 3 resistors, that's not necessarily the best ideal situation to analyze. We want to think of this as just one small clumped element for a resistor. So what we can do is we can find the equivalent resistance of all these resistors together. And we say that the net resistance of all these resistors is just the sum of the three resistors. That is one of the easy things about a series connection, is that if you connect all resistors like this, the total resistance of the chain is the same as the sum of all these three resistors. Now, another kind of combination that you can see is a parallel combination, like over here. As you can see that the main line that is coming from the power source, which isn't drawn here, branches off into three resistors right here. And since the resistors are branching off, what also ends up happening is that the current branches into each of these resistors. All right. And at the end, all the current meets down here and it flows back into the battery and it continues to repeat the loop. So, and just like I said, elements here, or in this case, resistors here, are connected in a branch. And the equivalent resistance of this kind of a layout is, well, a little bit more difficult to calculate. The inverse of the total resistance is the sum of the inverse of individual resistances. So this expression right here. All right. Now, these were a little bit of simple circuits. Now, what happens ending up in the electronics industry is something much more complicated than this. Now, well, over here, what I have is an example circuit of things that we get to see in the electronics industry. Now, this over here is called an operational amplifier. It takes two inputs, and the output is an amplified version of the difference of the two inputs right here. So and this is the technical way of labeling these inputs. We call one of them VID over 2. The other one is negative VID over 2. VID just stands for a differential input voltage, or voltage input differential as we end up writing it here, right? And VO represents an output voltage. The reason why we do this is compared to the other amplifier is that this kind of amplifier is very good at filtering out any kind of noise that may appear from any other source in the surroundings, right? So this is one of those circuits. There's many kinds of different circuits like this that exist out there. This is just an example that I wanted to share. And as we draw close to the end of this presentation, what I have here is the discussion of going from a paper drawing of the circuit, drawing similar to this one, or this one right here, from this drawing to the actual physical implementation of a circuit. So what happens is that the first thing that we do is that we propose a design, a paper design similar to the one that you saw on the previous slide. And once you have a paper design, you don't know if it's going to necessarily work or not. So what you do is you use simulation softwares. A few common ones are Cadence OrCAD, Altium Designer. There are many out there, but these are just a couple of the most common ones. So what we do is we design, or we draw the same design on these softwares and we run simulations. What happens then is if we are getting expected results, we move on. If we don't get expected results, we just try to keep changing things and make the circuit have more desirable properties based on what you want the circuit to achieve. So let's suppose we have moved on, we have gotten all the desired results from the circuit, it's behaving exactly as it should. So once that happens, what we do is we take what is called a breadboard and we design the circuit on that. Now, a breadboard is a physical tool. Let me see if I can show this over here on my screen. So over here, I'm holding what is called a breadboard. So the benefit of using a breadboard is that it has these holes over here, which hopefully you're able to see. Sorry about the background. So what you can do is simply take an element. I have a wire right here and pop it into this hole right here. And similarly, you're going to put all of the elements in. And once you do that, you can run the circuit. You can use tools like multimeters, oscilloscopes, and any other tool that you need to test whether the circuit is working fine. Once you do that, all you have to do is pull the components pull the components out and disassemble the circuit, and you can reuse the breadboard as many times as you want. It's one of the best things about using the breadboard, that you can easily put circuits together and you can reuse it as many times as you want. So once you get the circuit to work as you want it to work, what you can do is, oh, also I had a drawing of a breadboard here, which I neglected to put up before. But basically what you're doing is you're putting your elements into these holes right here. And when you're done testing the circuit, you can pull the circuit back out. So once we are satisfied with the physical circuit, we go back to our computer to design what is called a printed circuit board, or PCB. And basically what a PCB is, it's a much more compact version of the circuit. It doesn't have wires and elements sticking out of it. It's almost two-dimensional. It is the fancy kind of green circuit boards that you get to see when you open any kind of electronic gadget. So what you do is go onto the computer, put a design together for that, and once you send that design to the printer, it comes back printed. What you can do is solder each component onto the PCB. Now, what ends up happening is that once you are satisfied with the product and it's ready to be launched, usually what's going to end up happening is that you're going to manufacture thousands or millions of that component. So soldering that is going to be very tedious. So what ends up happening is that most of the soldering work for PCBs is done by robots or machines these days. All right. So on this final slide right here, I have something that is kind of put together from what you learned about last time about the Arduino. So what we have here is a circuit that has been designed using the Arduino. This is one of the projects that students did in ENG3, the class where I TA. This project is called the Love-O-Meter, and basically what that is that we are measuring love as a function of temperature. The more you're in love with someone, the higher your body temperature tends to go, is what we are proposing with the circuit. So what happens here is that we have a temperature sensor in the circuit right here. We have a few LEDs connected to these resistors down here. Remember, these resistors are to regulate the amount of current flow. So what happens is that a person would put their hand on this temperature sensor, and if their body temperature isn't too high, the LEDs aren't going to turn on. If the temperature is a little bit high, one LED is going to turn on. And based on what the temperature is, 2 or 3 LEDs might also be turning on. So this is a small little thing that is done in that class, which I wanted to show as a demonstration to put together some things that we learned in the past week and what we discussed today. So that is pretty much all that I had for this presentation. Since we have some time left over, there's a little bit of time left over for questions, but yeah, that is pretty much it from me. Thank you so much for listening.
Great. Thank you so much, Ron, for presenting. We really appreciated you sharing your knowledge about circuits. And thanks to everyone who tuned in on YouTube.
Thank you for the opportunity.